Have you ever felt like you're just drowning in information, trying to keep up, but it's almost impossible?
Oh, absolutely. It's a constant flood.
Especially with something like artificial intelligence, right? It's changing so fast, and it's kind of sneaking into our lives everywhere.
Yeah, often without us even noticing.
So AI is the big topic today. We're doing a deep dive.
Exactly. We've got this fantastic AI course from Ederica, and our mission today is basically to pull out the absolute must-know stuff for you, give you that shortcut to really understanding it.
Okay.
We'll look at, where AI came from, try to demystify things like machine learning, deep learning, make sense of it all.
And show where it pops up in the real world.
Definitely. Some surprising places. The aim is clarity, maybe a few aha moments without the overwhelm.
Perfect. We want you to walk away feeling like you've really got a handle on it. So yeah, clear structure, maybe some surprising facts, knowledge without the headache. Okay, let's unpack this then.
Let's do it.
So AI is obviously huge now, but to really get it, we probably need to look back a bit, right?
Mm-hmm.
Where did this all start?
Yeah, and it's funny, the idea of AI isn't new at all. It goes way, way back.
Like how far back?
Ancient Greece, believe it or not. Think myths, like Talos.
Talos.
Yeah.
Giant bronze guy, guarding Crete.
It's the one, an animated warrior. So even then, people were pondering, mechanical beings, artificial life. The concept was there.
Wow. Okay, so fast forward a bit. When did it become more scientific?
Right. Jump to the 20th century. 1950 is a key year. Alan Turing.
The codebreaker guy.
Yep. He wrote this seminal paper speculating about machines that could actually think. And that led to the famous Turing test.
Ah, the test to see if a machine can fool you into thinking it's human.
Exactly. And what's kind of wild is even now, all these decades later, no machine has definitively fully passed it. Shows you how high that bar really is.
So Turing set the stage. What came next?
Well, almost immediately, 1951, you get the first hints of game AI.
Games, like computer games.
Sort of the ancestors. Christopher Strachey wrote a checkers program. And there was a chess program around then, too, early days. But it was computers trying to compete with human strategy.
Okay, checkers and chess. Then what?
Then comes 1956. This is arguably the most important year.
Why is that?
Because that's when John McCarthy actually coined the term artificial intelligence at the Dartmouth conference. That's really the official birthday of AI as its own field.
Got it. So the name was born, and things started picking up speed.
Definitely. Milestones started popping up. 1959, MIT opens the first AI lab, still running today, actually.
Wow.
1960, you see the first robot on a General Motors assembly line. Practical application.
Right, automation.
And 1961, the first chatbot, Eliza.
Eliza. I've heard of that. It was like a therapist, right?
Kind of, yeah. Very simple by today's standards, but you can draw a direct line from Eliza to, Siri and Alexa today. It's the ancestor.
That's fascinating. So from these early steps, when did AI start doing things that really made people sit up and take notice?
Good question. There were some major moments that captured the public imagination. 1997, IBM's Deep Blue beating Garry Kasparov at chess.
Oh, yeah, that was huge. Man versus machine.
Exactly. A massive symbolic victory for AI. Then, 2005, Stanford's robotic car, Stanley, won the DARPA Grand Challenge. A big step for self-driving tech.
Right, navigating a desert course on its own.
Yep. And 2011, another IBM moment, Watson winning Jeopardy!
Against the best human champions. That showed AI could understand natural language, nuances, puns.
Precisely. It wasn't just calculation, it was understanding complex questions.
So it's this incredible journey, really, from myths and early tests to becoming this, central technology. The growth since the 50s has been kind of exponential, hasn't it?
Absolutely. It's gone from niche research to something fundamentally reshaping our world.
Which brings us to, the big question. AI has been developing for over half a century. Why the explosion now? Why is it suddenly so dominant, so important?
That's the key question, isn't it? And it's not just one single thing. It's more like a perfect storm of factors hitting all at once.
Okay, like what?
Well, first off, sheer computational power. It's just exploded, especially with GPU's graphics processing units.
The things are video games.
Exactly. They turned out to be perfect for the kind of parallel processing that deep learning needs. Suddenly, complex AI models that were theoretical became practical, deployable in everyday life.
So faster chips basically unlocked it.
Massively. That's factor one. Factor two, data. Just unbelievable amounts of data.
Right. We're all generating it constantly.
Constantly, like 2.5 quintillion bytes a day globally.
Yeah.
By 2020, it was something like 1.7 megabytes per second per person.
Yeah.
Social media, phones, sensors.
Wow, and AI needs that data.
It feeds on it. AI learns from data. All this data is the raw material needed to train AI agents, whether it's for recommending products or spotting patterns. Without massive data sets, AI doesn't get smart.
Okay, so more power, tons more data. What else?
Better algorithms. We've gotten much smarter about how machines learn. We're using techniques, often based on neural networks, that are just more effective at finding patterns, making predictions quicker, and, crucially, with better accuracy.
So the software got smarter, too.
You got it. And the final piece, investment. Huge investment.
Money pouring in.
Billions. From universities, governments, startups, and especially the tech giants, Google, Amazon, Facebook, Microsoft. They all see AI as fundamental to the future. It's driving innovation, creating whole new economies.
So it's the power, the data, the smart algorithms, and the money all coming together right now.
That's the confluence. That's why AI is everywhere right now.
Which means it's definitely the right time for all of us, for you listening, to really understand what it is. So here's where it gets really interesting. How do we define AI simply?
Well, going back to McCarthy in '56, he called it the science and engineering of making intelligent machines.
Okay.
A good working definition today is maybe. The theory and development of computer systems able to perform tasks that normally require human intelligence.
Like seeing, hearing, deciding things.
Exactly. Visual perception, speech recognition, decision-making, translating languages, stuff humans do.
So basically, it's about getting machines to act, well, human-like.
In a nutshell, yeah. Getting
Yeah.
machines to work and behave like humans in certain ways. And they do it in so many areas.
Let's talk applications. You mentioned Google search.
Yeah, perfect example. You start typing and it predicts what you want based on your history, location, maybe even age. That's AI trying to anticipate your needs, learning your patterns.
Okay, what else? Finance.
Oh, big time. JP Morgan Chase has this thing called coin contract intelligence. Uses AI, machine learning, image recognition to analyze legal docs.
How much faster is it?
Get this. Reviewing 12,000 agreements manually took over 36,000 hours. AI did it in, quote, a matter of seconds.
Wow, that's transformative.
Totally. Think about healthcare, too. IBM's Watson technology used in hundreds of hospitals. There was a case in 2016. It diagnosed a rare leukemia by comparing the patient's data against like 20 million oncology records. Super fast.
Incredible. Saving lives, potentially.
Essentially, yeah. Or Google's AI eye doctor project in India. It analyzes retinal scans to spot diabetic retinopathy early. Makes screening much more accessible.
Okay, so finance, healthcare,
Yeah.
social media must use it a ton.
Absolutely. Facebook's face recognition for tagging photos. That's AI.
Auto-tagging.
And Twitter uses AI to find hate speech or terroristic content. They found something like 300,000 accounts linked to terrorism, and AI flagged 95% of them automatically. The scale is immense.
Virtual assistants. Siri, Alexa. They're obvious examples.
Very obvious, yeah. And getting more sophisticated. Remember Google Duplex a few years back?
The one that could make phone calls and sounded totally human, with the ums and ahs.
It's the one. It added those human filters so effectively people couldn't tell it was a machine. Slightly creepy, maybe, but technically amazing.
And self-driving cars. That's pure AI, right?
Definitely. Computer vision, image detection, deep learning, all working together so the car can see and navigate. Elon Musk is always talking about Tesla's AI pushing towards fully autonomous driving, robo-taxis.
It's still a way off, maybe, but the AI is central.
Absolutely. And even simpler stuff like Netflix recommending movies based on what you watched, AI, Gmail filtering spam, AI, again, looking for those telltale words like lottery or full refund.
It really is woven into the fabric of our digital lives, isn't it? Often completely invisible.
Exactly. And understanding the types of AI helps make sense of it all. There are basically 3 evolutionary stages people talk about.
Okay, what's stage 1?
Stage 1 is artificial narrow intelligence, or ANI, sometimes called weak AI. This is AI that's designed for one specific task.
Like playing chess or recognizing faces or driving a car.
Precisely. And this is the crucial point. This is the stage we are in right now. Everything we just talked about, Alexa, Google search, self-driving cars, AlphaGo, it's all ANI. They operate within a predefined range. They don't have general smarts or self-awareness.
Okay, so ANI is what we have now. What's the next theoretical stage?
That would be artificial general intelligence, or AGI. Strong AI. This is the idea of a machine that can perform any intellectual task a human can.
So wouldn't just play chess, it could also write a novel or compose music or hold a deep conversation.
Exactly. True flexibility and adaptability, like a human. And despite how powerful machines seem processing millions of documents in seconds, they can't do simple human things like, walk into the living room and turn on the TV because they decided they wanted to watch something. That general reasoning isn't there.
So even super smart systems like AlphaGo Zero, which taught itself Go, that's still not AGI.
Nope. Still narrow AI. It's incredibly good at Go, but it can't do anything else. No machine has achieved strong AI yet.
Right, and the final stage.
Yeah.
The sci-fi stuff.
That's artificial superintelligence, ASI. This is where AI capabilities would surpass human intelligence in basically all aspects: logic, creativity, social skills, everything.
Like Skynet and Terminator.
Pretty much the classic depiction, yeah. It's purely hypothetical at this point. Some people speculate it could happen by, say, 2040, but...
Yeah.
Well, let's just say we should be thankful it's hypothetical for now.
Okay, so summarizing that, neural intelligence is all that actually exists today. Everything we interact with is ANI. General and superintelligence are still future possibilities, maybe.
That's the current state of play, yeah.
So what's the engine behind all this ANI? How do these machines actually learn to perform these tasks? Does that get us into machine learning?
It does. Machine learning, or ML, is absolutely fundamental here. Think of AI as the broad goal mimicking human intelligence. Machine learning is a primary method or subset of AI for achieving that goal.
So AI is the umbrella. ML is a tool underneath it.
Exactly. ML is about feeding data to a machine and enabling it to learn from that data to make decisions or predictions without being explicitly programmed for every single scenario. It's how AI systems acquire their capabilities.
And why is ML itself so vital now? We talked about data and power for AI generally, but for ML specifically.
It's largely the same drivers, but focused on the learning aspect. That massive increase in data generation we mentioned, ML is what lets us actually use it, to structure it, analyze it, find the useful insights buried within that excessive production.
So ML makes the data useful.
Right, and it leads to vastly improved decision-making. ML algorithms can forecast sales for a business, predict stock market trends, identify risks, things that require finding subtle patterns in data.
Patterns humans might miss or take way too long to find.
Precisely. Uncovering hidden patterns and trends is a key strength. What might take a human analyst days of sifting through spreadsheets, an ML algorithm can often do in seconds.
And it tackles complexity.
Hugely complex problems, from medical research like finding genetic markers for diseases like ALS, to the intricate navigation needed for self-driving cars, even analyzing signals from space to find distant stars. ML provides the tools for problems that were previously intractable.
So yeah, you're right. It really is all about the data.
Yeah.
ML is the key to unlocking its value.
Could have said it better myself. The term machine learning actually goes back to 1959, coined by Arthur Samuel.
Okay.
And a simple way to think about it is a subset of artificial intelligence which provides machines the ability to learn automatically and improve with experience without being explicitly programmed to do so. It's getting machines to think by learning from data.
Okay, so how does that learning process actually work? If I wanted to build an ML model, say, to predict if it will rain tomorrow, what are the steps?
Great example. There's a pretty standard workflow, usually around 7 key steps.
Step 1.
Define the objective. Be crystal clear about what you're trying to achieve. Predict rain. Yes or no, that's a classification task. What data might predict it? Temperature, humidity, pressure. Those are your predictor variables. Rain is your target. Clarity here is vital.
Okay, know your goal. Step 2.
Data gathering. You need the historical data, past records of temperature, humidity, pressure, and whether it actually rained on those days. This can be tough manually, but thankfully there are great online resources like Kaggle with prepackaged data sets.
Got it. Find the data. Step 3.
Data preparation, or, more commonly, data cleaning. This is often the hardest part. Real-world data is messy, missing values, weird outliers, duplicate entries, maybe irrelevant columns. You have to fix all that.
Why is it so hard?
Because bad data leads to bad models. There's a saying, garbage in, garbage out. Seriously, surveys show data scientists spend up to 80% of their time just cleaning and preparing data. It's critical, but laborious.
Okay, clean the data. Step 4.
Exploratory data analysis, or ED. This is where you play detective. You visualize the data, look for patterns, trends, correlations. Maybe you plot temperature against rain and see a clear relationship. EDA helps you understand the data before you model it.
Explore, look for clues. Step 5.
Building the model. Now, you use the insights from EDA. You typically split your clean data, maybe 80% for training the model, 20% for testing it later. You choose an appropriate ML algorithm for rain prediction. Yes, no, you'd pick a classification algorithm. The training data teaches the model the patterns.
Train the model.
Yeah.
Step 6.
Model evaluation and optimization. How good is the model you built? You use that 20% testing data the model hasn't seen before to check its accuracy. Is it predicting rain correctly? If not, you might need to tweak the model, tune its parameters, maybe use techniques like cross-validation to improve its performance and ensure it generalizes well.
Test and improve. And finally, step 7.
Making predictions. Once you're happy with the model's performance, you deploy it. You feed it new data, like today's weather conditions, and it makes the prediction rain or no rain tomorrow.
That's a really logical flow. Define, gather, clean, explore, build, test, predict. Takes you right from the idea to the answer.
Exactly. It's a structured way to harness the power of ML.
Now, you mentioned choosing an algorithm. How do machines actually learn? Are there different styles of learning?
Yes, there are 3 main paradigms or styles: supervised, unsupervised, and reinforcement learning.
Okay, let's start with supervised. What's that?
Supervised learning is like having a teacher. You train the machine using data that is already labeled with the correct answers.
Labeled data.
Yeah. So if you want to teach it to recognize pictures of cats and dogs, you feed it thousands of pictures, and each one is labeled cat or dog. The machine learns the patterns associated with each label. The output it produces is also a prediction of a label.
So you're supervising its learning by giving it the answers up front in the training data.
Precisely. It's used for problems like regression predicting a continuous value, like a house price, and classification predicting a category, like spam or not spam, or cat or dog.
Okay, that makes sense.
Yeah.
What about unsupervised learning? No teacher this time.
Exactly. With unsupervised learning, you give the machine unlabeled data. It has to find patterns and structure on its own without any predefined answers, like a smart kid figuring things out by observation.
How does it do that?
It looks for similarities and differences in the data and groups similar items together into clusters. It identifies the inherent structure.
Can you give an example?
Think about Netflix. They might use unsupervised learning to group users with similar viewing habits, ages, or locations. They don't tell the algorithm what the group should be beforehand. The algorithm discovers these natural groupings itself, which then helps with recommendations. It solves problems like association, finding rules like people who buy X also buy Y, and clustering.
Okay, learning with labels, supervised, versus learning without labels, unsupervised. What's the third one? Reinforcement learning.
Right. Reinforcement learning is quite different. It's about learning through trial and error based on rewards and punishments.
Like training a pet.
Kind of. You have an agent, the learner, acting in an environment. The agent performs actions, and for each action, it receives feedback, a reward if it did something good, a penalty if it did something bad.
So it learns by trying things and seeing what happens.
Exactly. Imagine dropping someone on a desert island. They learn to survive by trying things, eating this berry, good reward, touching that snake, bad penalty. The goal of the agent is always to maximize its total cumulative reward over time.
Where is this used?
It's huge in robotics, game playing. Think AlphaGo, learning to play Go by playing millions of games against itself and learning which moves lead to winning the reward, or training a robot to walk. It's constantly adjusting its actions based on the feedback.
Is there a trade-off involved?
Yes. A key concept is the exploration versus exploitation trade-off. Should the agent stick with actions it knows, give a decent reward, exploit, or try new, unknown actions that might lead to an even bigger reward, explore? Balancing that is crucial.
Fascinating. Supervised, unsupervised, reinforcement. 3 very different ways machines can learn depending on the data and the goal.
Right, and within those styles, especially supervised and unsupervised, there's a whole toolkit of specific algorithms engineers use.
Okay, so let's touch on some of those algorithms. You mentioned problems fall into regression, classification, or clustering.
Yep. Regression predicts a continuous number, like price or speed. Classification predicts a category, yes, no, spam, not spam, cat, dog, mouse. Clustering groups similar things together without predefined labels.
So what's a common algorithm for, say, regression?
The classic is linear regression. It assumes a linear relationship between your input variables and the continuous output variable you're trying to predict. It basically draws the best fitting straight line through your data points. Think predicting house price based on square footage, often a roughly linear relationship.
Simple and interpretable. What about classification?
A very common one is logistic regression. Now, the name is confusing because it has regression in it, but it's actually for classification.
Why the name then?
Because mathematically, its underlying technique is related to linear regression. But instead of outputting a number directly, it outputs a probability between 0 and 1 using a sigmoid or S-shaped curve. You then use a threshold, like 0.5, to classify the outcome. Example, if probability 0.5 predict yes, otherwise no. Great for binary outcomes.
Okay, logistic regression for categories. What else for classification?
Decision trees are very popular because they're easy to understand. They look like flowcharts or, well, inverted trees.
How do they work?
You start at the root node with a question about a feature. The example is humidity 70%. Based on the answer, yes, no, you follow a branch to another question and so on until you reach a leaf node which gives you the final classification. For example, rain or no rain. It splits the data based on the most informative features at each step.
So it's like playing 20 questions with the data.
That's a great analogy, and to make them more powerful, you can use a random forest.
Forest, as in many trees.
Exactly. A single decision tree can sometimes be inaccurate or overfit the training data. A random forest builds hundreds or thousands of different decision trees, each trained on a random subset of the data and features. Then it combines their predictions, typically by taking a majority vote, to get a much more robust and accurate classification. It's the wisdom of the crowd, but for trees.
Clever. Any other classification mainstays?
Naive Bayes is another important one. It's based on probability, specifically Bayes' theorem. It calculates the probability of an outcome given certain features.
Why naive?
Because it makes a naive assumption that all the input features are independent of each other, which often isn't true in reality. But despite this simplification, it works surprisingly well, especially for text classification like spam filtering.
Oh, okay. What about k-nearest neighbors? KNNN.
KNN is interesting. It's simple and can be used for both classification and regression. It's called a lazy learner.
Lazy.
Because it doesn't really build a model during training, it just stores all the training data. When a new data point comes in, it looks at its k closest neighbors in the training data based on distance and assigns the new point the most common class among those neighbors for classification, or the average value for regression.
So it classifies based on similarity to nearby known points. How do you choose k?
That's a key parameter. Choosing the right k often involves testing different values and seeing which performs best, maybe using something like the elbow method to find a good balance.
Right. One more. Support vector machine or SVM. It sounds complex.
It can be, but the core idea is elegant. For classification, SVM tries to find the best possible boundary or hyperplane that separates the different classes in your data.
Best possible boundary.
Meaning the one that has the largest margin, the biggest possible gap between the boundary line and the closest data points from each class. Those closest points are called the support vectors, hence the name. Maximizing this margin often leads to better generalization.
What if the data isn't separable by a straight line?
That's where SVM gets clever. It can use something called the kernel trick to project the data into a higher dimension where a separating hyperplane can be found. Think of taking tangled strings in 2D and lifting them into 3D so you can easily separate them.
Okay, wow. So that's a diverse toolkit of algorithms for different learning styles and problem types. But even with these powerful ML tools, you mentioned limitations. What couldn't they handle well?
Right. Traditional ML, despite its successes, started hitting walls with certain types of problems. Two big ones stand out. First, high-dimensional data. Think about images. A simple image can have millions of pixels, or text analysis with tens of thousands of unique words. Traditional ML algorithms often struggled to cope with the sheer number of input features, the curse of dimensionality. Performance degraded, computation became infeasible.
Too many inputs overwhelmed them. What was the second limitation?
Feature extraction. This was a huge bottleneck. For ML to work well, you usually needed a human expert to figure out which features in the raw data were important for the task, and then engineer those features manually.
Like telling the cat detector algorithm to look for pointy ears and whiskers.
Exactly. The algorithm's success depended heavily on the quality of these handcrafted features. For complex tasks like recognizing thousands of different objects or understanding subtle nuances in language, manually designing good features became incredibly difficult, if not impossible.
So ML needed help figuring out what to look for in complex data.
Precisely. And this is where deep learning really shines.
Okay, so deep learning steps in. What is it, fundamentally?
Deep learning is essentially a subfield of machine learning. It uses algorithms inspired by the structure and function of the human brain specifically, artificial neural networks with multiple layers,
Multiple layers.
hence deep.
That's the key idea. And the magic is that these deep networks can automatically learn relevant features directly from the raw data. They overcome that feature extraction bottleneck. They learn hierarchies of features, simple features in early layers, combined into more complex features in deeper layers.
So instead of telling it to look for whiskers, it learns on its own that whiskers are important for identifying cats just by looking at thousands of cat pictures.
You got it. It learns the important representations by itself, with much less human guidance. It mimics how our brains seem to process information.
How closely does it actually mimic the brain?
Well, it's an inspiration, not a direct copy. The basic unit is the artificial neuron, or perceptron, inspired by biological neurons.
How does a perceptron work? It receives multiple inputs, just like dendrites receive signals. Each input has an associated weight, signifying its importance. The perceptron sums up these weighted inputs. If the sum exceeds a certain activation threshold, like a neuron firing, it produces an output. There's usually a bias term, too, which helps adjust the threshold.
So inputs, weights, sum, activation.
That's the core. But a single perceptron is limited. It can only learn simple linear patterns.
So you need more.
Yes, you connect them together into networks. The simplest is a single-layer perceptron, just input and output layers. But the real power comes from multi-layer perceptrons, MLPs.
Adding layers in the middle.
Exactly. You add one or more hidden layers between the input and output layers. This allows the network to learn much more complex, nonlinear patterns in the data. This layered structure is what makes it deep. Information typically flows forward from input through hidden layers to the output, hence feed-forward networks.
Okay, so you build this deep network. How does it actually learn? How do the weights get set correctly?
That's where the crucial algorithm called backpropagation comes in. It's how the network learns from its mistakes.
Learning from mistakes. How?
Okay, so initially, the weights in the network are set randomly. You feed the network some training data, it makes a prediction, and you compare that prediction to the actual correct answer. You calculate the error. Backpropagation then works backwards through the network, figuring out how much each weight contributed to that error.
And
then it adjusts those weights, tiny step by tiny step, in a direction that reduces the error. You repeat this process over and over with lots of data, and gradually the network learns the optimal weights to make accurate predictions. It's like tuning thousands of knobs to minimize the overall error.
So it's constantly refining itself based on feedback about its errors.
Precisely. That's the heart of how most deep neural networks are trained.
Are there different types of these deep networks for different jobs? You mentioned feed-forward. Do they have limitations?
They do. Standard feed-forward networks treat each input independently. They don't have any memory of task inputs. That's fine for some tasks, but not for sequential data, like language, where the meaning of a word depends on the words that came before it.
Right, like reading a sentence.
Exactly. For sequences, you need networks that can remember past information. That's where recurrent neural networks, RNNs, come in.
How do RNNs work?
They have loops. The output from one step is fed back as input to the next step. This creates a sort of memory, allowing them to process sequences and understand context over time. They're used a lot in natural language processing, speech recognition, time series prediction, like stock markets, anywhere order matters.
Okay, so RNNs for sequences. What about images? You mentioned deep learning is good at that too.
For images, the dominant architecture is the convolutional neural network, CNN.
Convolutional.
Yeah. CNNs are specifically designed to process grid-like data, like pixels in an image. They use a special operation called convolution, which involves sliding small filters over the image to detect features like edges, corners, textures.
So they look for local patterns.
Exactly. Unlike fully connected networks where every neuron connects to every neuron in the next layer, which gets computationally insane for images, CNNs connect neurons only to a small local region in the input. This makes them much more efficient and helps them learn hierarchical features, simple features first, then combinations of those features to detect more complex objects. They're behind most modern computer vision successes.
Image recognition, self-driving car vision.
All heavily reliant on CNNs. Image analysis, segmentation, even compression.
Okay, so we have these powerful learning techniques, ML, and especially deep learning with its various network types. This brings us to language. How do machines grapple with human language? It seems incredibly complex.
It is incredibly complex, and that's the domain of natural language processing, or NLP, and also text mining.
What's the difference?
Think of text mining as the broader goal, analyzing text data, spoken or written, to extract meaningful insights and knowledge. NLP is a key component or enabler of text mining. NLP focuses on enabling computers to understand, interpret, and manipulate human language itself. It's about bridging the gap between human communication and computer understanding.
Why is this so important now?
I've
Again, is it the data explosion?
Absolutely. Remember that most data being generated is unstructured. A huge chunk of that is text and speech, emails, social media, reports, customer feedback. NLP is essential to unlock the value hidden in all that language data.
So NLP helps machines read and make sense of our words.
Exactly. Converting our messy, nuanced language into a structured format computers can work with, like numbers or vectors.
What are some everyday NLP applications we might not even think about?
You use them constantly. Google's autocomplete or spell check, that's NLP. Gmail's spam filter understanding the content of emails. NLP.
Yeah.
Sentimental analysis is a huge one. Automatically determining if a product review, tweet, or news article is positive, negative, or neutral. Businesses use this constantly to gauge public opinion.
Right, understanding feelings from text.
Chatbots for customer service,
Yeah.
pure NLP trying to understand your questions and generate helpful responses, speech recognition on your phone, NLP converting your voice to text. Even online ad recommendations based on your browsing or search terms involve NLP understanding language.
It's everywhere. So what are some of the core techniques NLP uses to actually process language? How does it break it down?
There are several fundamental steps. One of the most basic is tokenization.
Tokenization.
Yeah, just breaking down a piece of text into smaller units or tokens.
Yeah.
Usually this means splitting a sentence into individual words or maybe punctuation marks. So NLP is cool, it becomes tokens. NLP is cool. It's a first step for most other processing.
Okay, break it into words. What next?
Often you'll do stemming or lemmatization. These are techniques to normalize words.
Normalize.
Yeah, reduce different forms of a word down to a common base form. Stemming is a cruder method. It just chops off ends of words. So running, runs, ran might all become run, but sometimes it creates non-words.
Like computation becoming compute.
Exactly. Lemmatization is smarter. It uses vocabulary and grammatical analysis to return the actual dictionary base form, the lemma. So running, runs, and ran would all correctly become go. It's usually preferred if you need grammatical accuracy.
Okay, standardize the words. What else?
Removing stop words. These are very common words like the, a, is, in, and. They often don't carry much specific meaning for analysis, so they're filtered out to focus on the more important words.
Get rid of the noise words.
Pretty much. And then to represent the text numerically, you might create something like a document term matrix.
What's that?
It's basically a big table. Rows represent documents like emails or reviews. Columns represent unique words after tokenization, lemmatization, stop word removal. And the cells contain a count or score showing how often each word appears in each document. This matrix gives algorithms a structured numerical way to see the content of the texts.
So tokenizing, normalizing words, removing common words, and then counting word frequencies in a matrix. These steps help turn language into something algorithms can analyze.
Exactly. These are building blocks that enable higher-level tasks like sentiment analysis, topic modeling, machine translation, and much more. It's how machines start to understand us.
Wow. We have covered an incredible amount of ground here, from Greek myths and Alan Turing asking if machines can think,
Right, through the birth of AI, the key milestones.
to why it exploded recently, the power of the data, the algorithms, the investment.
And seeing it everywhere, from search engines to healthcare to how you get movie suggestions.
Then we really unpack the engine. Machine learning is a subset of AI, the different learning styles, supervised, unsupervised, reinforcement.
And the toolkit of algorithms like regression, decision trees, SVMs.
Before hitting the limits of traditional ML and seeing how deep learning, inspired by the brain with its neural networks and backpropagation, took things to the next level.
Especially with specialized networks like RNNs for sequences and CNNs for images.
And finally, landing on natural language processing. How machines grapple with the complexities of human language using techniques like tokenization and lemmatization.
Yeah, it's been quite a journey through the core concepts. The aim, really, was to give you, the listener, that solid foundation, that shortcut to being genuinely informed about this hugely important field. Because understanding these ideas, AI, ML, DL, and LP, it's becoming essential just to make sense of the world around us, how technology is changing and where it might be headed.
Absolutely. So maybe the final thought to leave you with is this. Knowing all this, what does it mean for your future? How will these increasingly intelligent machines continue to shape how you learn, how you work, how you connect with others?
Yeah. Something definitely worth pondering.